Hello, guys. Welcome to this session. Lovely to have you all here. So just to go really quick into the business of the day. Today, we're going to be talking about building production-grade real-time voice agents. So this is all about the agentic pipeline, the agentic AI agentic system. And we're going to be using the case study of a production-grade architectural workflow that involves LiveKit, LangChain, GPT-4, Flutter, and for banking apps. So we're using this as our case study to explore building production-grade real-time voice agent system. Once again, my name is Nwadike, and I am an AI engineer walking you through the flow for today. So into the business, what we're looking at building is a platform where we have real-time voice agents that stream audio from a mobile app, transcribes that in real time, uses GPT-4 for reasoning, executes via LangChain, streams the text-to-speech back instantly. This is not a regular chatbot. This is not a chatbot. This is a distributed low-latency AI voice automation system. And the high-level architecture of what we're looking at, its architectural model is we're going from a client layer, which is our Flutter app, that uses a microphone capture to get your voice input, translate that using the WebRTC connection, it's able to connect to the backend using the audio playback, and then has sessions, real-time layer, the LiveKit. This works through audio streams that have very low latency down to our AI orchestration, and then it hits our LangChain layer that is responsible for the agentic framework. And that LangChain communicates with any LLM interface, and those what we call a tool or function call, and also manages that in memory states, memory management, moves through intelligent layer, hits back our reasoning from our reasoning layer, which is our GPT, in this case, which is our LLM, in this case, GPT-4. And then it does a tool selection, looks for the right tool to call, and then gives back the response. You can also go through optional layers like the vector database, or you can go through conversation history via Redis, or via the Postgres, via a real-time database like Postgres, or via vector databases like ChromaDB that you can use to do that context injection into the entire workflow. Now, why LiveKit? Because in this workflow, we're looking at implementing LiveKit as the WebRTC. Given that we're dealing with voice agent, it's very sensitive that we have to look at latency. And in doing that, we have to use tools that support proper latency, the lowest possible time of communication in the transport layer. And so LiveKit gives us what we call a WebRTC, a web real-time communication client-to-client connection pipeline that improves that communication between two clients. So we're looking at real-time voice agents. Some of the challenges we have is that real-time voice agents usually fail without proper streaming infrastructure. And this is what LiveKit provides. We have WebRTC ultra-low latency streaming built for selective forwarding unit, room sessions, abstractions, automatic reconnection, scalable multi-region deployment. And we're not using HTTP, we're using WebRTC instead. This is because HTTP request to response cycle, HTTP is mostly a request to response cycle, but the voice agent is continuous. So we need a continuous stream. It's bytes of data transported in real time and continuously. And we need that to be like that. That's why we need WebRTC to enable that bidirectional stream and end-to-end connection in real time. So now the next part is our client side, which we use WebRTC to connect to the server side. So we use Flutter as our case study in this voice agent pipeline. Now, Flutter basically is a hybrid framework for creating both mobile and web apps, and it's a framework built on that programming language. So what Flutter basically does is your mobile app, it does the capturing of the microphone, it encodes the video, it communicates with the WebRTC, it publishes the connections, it listens to agent audio stream, It does all the UI state management. It's critical front-end requirements, interrupt detection, push to talk, all the continuous end-to-end connection that the client needs to, or the user needs to communicate with the voice agentic pipeline. Flutter is now gives us that framework. It gives us that infrastructure, the framework infrastructure for us to be able to create apps that are able to automate voice workflows. Now we're looking at the real-time audio flow. This is the whole point about the voice agentic system. Like, it has to be real-time, it has to be in streams, and it's mostly audio. So when the user speaks, the Flutter app captures the PCM frames. It audio encoded with OPIS. Streams sent via WebRTC to a LiveKit room. The backend agent subscribes. The speech-to-text transcribes partial tokens. The GPT-4, as the reasoning framework, processes this stream and sends that back as text-to-speech. The Flutter then plays it back, and that's how everything goes in synchrony without any blockage time, no block time, no delay time. Everything streams, nothing waits for completion. It's all real-time stream end-to-end. Now let's look at the speech-to-text integration. Has anyone done something that involves speech-to-text before? Has anyone used any speech-to-text framework? People exploring AI space and AI models. Has anybody used any speech-to-text AI model? So I'm going to give us one, which is the Whisper from OpenAI. It basically captures your speech and transcribes that to text. The whole point is that your speech is not directly reasoned on as audio. So it has to be translated or transcribed to text, which is what the LLMs we have today, the deep neural network based LLMs we have today, all function on reasoning on text or passing text through the LLM pipeline. So your speech is captured, translated into text, passed through an LLM. Now that whole framework is coordinated using an agentic framework like example LangChain, and the connection you have in for the real-time audio synchrony or synthesis for WebRTC using LiveKits I previously mentioned. Now, when that text is reasoned on, it now passes that back, the returned output, which has been reasoned on as text, not as audio, but this time now it needs to be returned back to the user as text. That is why we now need a different model to also interpret that back to audio, and then the user receives the audio. So it's all like a synchrony of things, all multiple things working together at the same time and producing the perfect stream synchrony. And in this case study, we're using GPT-4 as our reasoning engine, and it's a very high level LLM tool, a very good model so far, and it competes. It outperforms in multiple benchmarks when it comes as compared to so many other models out there. So we use GPT-4 for intent detection because when you create, let's say, a microservice workflow, and a microservice-based agentic workflow, you might need to do intent classification to be able to know what, based on the task the user is trying to perform, we want to know what actual microservice chat system we want to communicate with. So it's all like a workflow, a connection of different pipelines that we use to implement this, and we always have to detect what is the task the user wants to perform. Now, when we detect that task detection is done. It's called intent classification, intent detection, and it is done by our LLMs, in this case, GPT-4. When we've been able to know what the user actually wants to do, the framework can then route that using tool calling, now routes that to the proper tool or function it's supposed to call to achieve that task. Now, let's look at the agentic orchestration framework, which is our LangChain framework, the LangChain tool. So LangChain basically sits between the speech-to-text, GPT-4, tools, memory, and text-to-speech. So it's the agentic framework that coordinates all these multiple parts, and it integrates to multiple different LLMs, and it has very good API interface, an SDK is that interface to multiple LLMs. You're not basically stuck to one particular LLM. You can use multiple LLMs. I don't know if anybody has heard about tool calling or function call. So this is yeah, absolutely. So this is very paramount when it comes to anything that has to do with AI agentic system. And most of all, for voice agentic pipelines, you need to make function calls. And tool calls basically are functions, or tools that basically functions that give the LLMs extra power. They give that agentic pipeline extra power to know things going on outside the circumference of its trained data. So we want to achieve, we want to get data from external APIs, from companies, from the internet. We use tools to call that. The LM just serves as the reasoning frame, does the reasoning, knows what function to call, and these functions pipe in or feed in data into the LLM, which now context injects. In this case, we're using GPT, which is a decoder-only model. So it just does automatic, autoregressive, complete text completion, character generation, and then token generation, and then it generates more token based on the context that it is received from the data it's been fed from the external APIs or external functions. So it's a very powerful reasoning framework, a very powerful tool. LangChain basically sits in the whole middle of all these pipelines. And this diagram here just shows us a very good illustration of what it actually does. So the user gives an input, the LangChain prompt template discovers pipes into GPT-4, and GPT-4 handles the tool calling. GPT-4 is also very good at tool calling, integrated to the LangChain agentic framework. And yes, if it's a tool call problem that doesn't need that, if it's a task that we have tools or we have functions to handle, the GPT-4 is smart enough and intelligent enough to be able to route to the proper function to call. And then it executes that tool, returns the result, and then continues in the loop. So it can happen in multiple iterations up until we've achieved the perfect state of the task to be performed. So this is the whole overview of the low-level architecture of how LangChain integrates with the LLMs and the agentic pipeline. So I hope you enjoyed it so far. I hope we've been able to have very good knowledge, very good understanding of how the LangChain helps in this pipeline flow. So let's look at example of a tool execution architecture. Example, a user says, in a banking workflow, a user says, send £500 to Sarah. Now, LangChain defines this. By integrating with the LLMs, is able to extract the context of the conversation. And it knows it's able to also JSON construct. It's able to construct JSON data. JSON, for people who do not know, that is a structure, data structure. So it's JavaScript object notation. So it's a data structure that is mostly used just like the YAML for transporting data via API. So it's a defined data structure format for data transportation. So from this conversation where the user says, send £500 to Sarah, the LangChain integrated with the LLM, in this case GPT-4 as our case study, is able to extract the name that it's, oh, we're trying to do a transfer of funds. And now what you have to take note is that we're looking at tool call execution, the tool execution architecture. It means that in our agentic pipeline, we have to define multiple tools that perform multiple tasks. And in this task, the way it's structured is that for every tool, for every function, tools that basically functions, as I explained previously, for every tool, you have to define what the tool does. You also have to define the request schema, the model of request it takes in, and the response payload too. So the schema of the request and the schema of the payload and the description of the function name, the function signature. With that information, piping that to our reasoning model, in this case GPT-4, in our LangChain agentic framework, we're able to orchestrate the tool call. And the system is able to know, for example, in this case of send £500 to Sarah, is able to know I'm getting the amount is this data format, the recipient is this data format, the account you're sending it to is this data format. It knows the data format, it knows the schemas, and it knows the intents of every function, and also knows how to reason to get the proper function that handles that request. So when we're doing streaming, given that we're very sensitive on latency when it comes to audio streams, given that it's like bytes or multiple spatial bytes of data, we have to be very careful when it comes to transporting streams of data over the internet. Because when we have so much bulk of byte size, obviously that leads to higher latency time because we have more transportation to do due to the bulk size of data. And that is why we stream this text-to-speech in chunks. Now we have a pipeline where the GPT-4 token stream is chunked using text in a text buffer. The text-to-speech engine gets that and it gets that into an audio chunk, into audio chunks, and that goes into the live kit WebRTC, and then that goes back to the playback. If user interrupts, it's able to know that to stop TTS immediately. So I've been using the word TTS, and I know some people might be confused. Who understands what TTS means? Because when you're talking about agentic frameworks and audio transcription, you have to understand what TTS means. Anybody? Perfect. I can see some very good indications that. So text to speech, TTS simply means text to speech. So it's responsible for taking any text and outputting that as an audio output, as a speech synthesized output. So if at any point of the agentic workflow in our voice agent, the user interrupts or he cancels the GPT-4 streams, or the system is able to refresh itself and rotate its sessions to be able to accommodate any user action during the pipeline. Very sensitive area is the memory architecture in LangChain. Very, very sensitive, because there needs to be a way that our reasoning framework is able to remember the conversation pipeline, the conversation stream, the conversation history. There has to be a way to feed previous conversations, because for every interaction, it's a one-time round trip. So it's a request response, and that's just a one-time round trip. There needs to be a way to inject the previous round trips that has been done in a session into the context of the current session. And that is where memory management comes in. LangChain fits very much perfectly into this by the architectural layer it provides to us. So we have session memory, the recent conversation turns. We have persistent memory stored in vector databases, or let's say your real-time databases like PostgreSQL. Then we have structured data, user financial records, secured backend. We have LangChain manages the memory injection into the GPT-4, token budget control, context window pruning. Without context pruning, cost explodes. And this is where LangChain fits very well with the LLMs to be able to prune the context as the conversation keeps going longer and longer. The context window keeps expanding, the tokens being reasoned on expand. And the way the LLMs work is that the more tokens are in your context window, the more cost, because now it takes more input data and it takes longer time to process. So in training all this, we have to be very careful. As once again, as I mentioned previously, the latency, we want very low latency. We want our conversations to occur in milliseconds, very fast. So once again, the latency, I've been mentioning latency. So let's look at the latency engineering of the agentic pipeline. So the target is about less than 600 milliseconds perceived latency. We want our conversations to happen really quick. So the time it takes for you to give a command and the time it takes to have an output, a response back, we want that to be really quick. And this is how we break it down. We have the audio transport done via LiveKit. We're looking at approximately 150 milliseconds, and we pipe that into our speech-to-text partial, approximately 200 milliseconds. That goes to GPT-4. Now we're looking at who's talking about TTFT. Anybody? So TTFT simply stands for time to first token. So we have so many latency parameters we use to measure optimization or efficiency of response calls or response cycles, request response cycles. And one of this, when it comes to the agentic AI frameworks, is the TTFT, the time to first token. So how long does it take from your conversation to when the LM actually produces a token output as a response? Because it usually happens when you're given the input data, input stream of audio, and it's reasoned on, the LM also produces an output stream of audio based on the reasoning context. So the very first initial token, based on whatever token indices or parameters or architecture it uses, what time, how long does it take to produce the very first token? And then we're also looking at giving that back to the user as an audio streamed output. So always once you reduce the message size, use smaller context window and preload our tools. So these are very multiple optimization strategies to reduce the latency time, and we do that by also having the very reduced or very optimal time to first token for our text to speech. Moving to the next, how do we handle interruptions? Because we're dealing with very real systems. We're not dealing with bots, you're dealing with human beings, and human beings obviously have the way they communicate. They have multiple ways they communicate. How do we handle interruptions during our agentic flow, during our communication flow? If the user is, for example, is saying, I want to send money to send £500 to Sarah, and during the conversation to and fro, is requesting for what's the account details, do you want to do it now? Is there a category for this? Is there a reference for this? During that whole communication pipeline, communication flow, note once again that during all this, we mentioned that it's always like a one-time trip for every speech to text response. And in the communication cycle, in the communication flow entirely, we have multiple communication cycles, and we have to have a way to manage the memory of the previous conversations and inject that to the current conversations. So having that, we understand that as the basis for communication to context inject info data. We're also looking at how do we handle interruptions. So we have a context injected data. We have previous conversations injected into our current flow. Given that we're also optimizing our latency and our TTS time to first token, we're also optimizing our latency time. Even given that, now we do our conversation or communication, and the user interrupt. He says something that needs to interrupt the system, or needs to interrupt the communication, or wants to cancel the transaction. For example, if you're doing a send funds or transfer request, how does the system handle this? Now, how we implement this is that the V agent detects new speech, the flow signals interruption, the backend cancels TPT stream, the text-to-speech playback stops, the conversation state updates, the agent restarts reasoning, the live key streaming nature makes this seamless. So the live key streaming nature makes this very seamless. So we're doing multiple stuff, when multiple activities, multiple executions, when the user tries to interrupt the conversation flow. But at the same time, this is all done very seamlessly that the user doesn't even know that all this is happening. These are all done in the backend. Which is the very beauty of the whole agentic pipeline, the agentic flow, and the tool calls and tool consumption, and the tool flow we use. Now, very importantly, the security architecture. The voice agentic system is a very crucial and sensitive sector, especially when it comes to our case study, the banking app. When it comes to banking systems, it's very sensitive that we make sure that we make sure that the user's communications from the transportation layer in the first place is very protected, and it's not tapped into by a third party to retrieve or gain access to information. Because during communication, the user, being human beings, can arbitrarily expose sensitive data or information. How do we secure that? So from the user point of view, so it's all like user experience and then infrastructure security. User experience security, infrastructure security, user data security. How do we secure all these layers? So voice agents increase risk surface, as I mentioned previously. The security layers, the JWT authentication. Who's heard about JWT before? JSON Web Tokens. Perfect. So JSON Web Tokens are used they're very good for authentication from our front end among multiple systems. So it can be our front end to our back end. But these are tokens generated from the user data, encrypted and signed, and can also be decrypted to identify what user owns that token. They can be refreshed, they can be rotated. So when it comes to all the authentication using JWT, we also have other tools we can use for that, but one of the most widely used is JWT, especially for client to server. We also have JWKS, which is more for microservice interaction, MTLS, and microservice to microservice security and communication. That's JWKS. But JWT, from our user side to the server, it works. The signed backend tool calls, the role-based access control, tool validation schemas, the red limits, the prompt injection filtering, guardrails, very important. We can also add transaction confirmation step, voice biometric optional layer. So we want to know once you do voice recognition first, even before starting any processing. We want to have secondary approval for high value transfers. So we want to like have approvals from users before. So given that you've had these multiple conversations before the end execution that completes the transfer, we want to be able to have the user's approval to make that work, to complete that flow, given that we've gotten the proper JSON context that we need. So zero trust, never trust LLM output blindly. We want to implement very zero trust system. We want to make sure that all our systems, our agentic system, our microservice system, front end to back interaction, LLM to user interaction, LLM to backend interaction, LLM to tools interaction, LLM to microservices interaction, microservice to microservices interaction. We want to make sure that all these are very much secured. So I hope we're all enjoying the class so far. I hope we're getting very good knowledge. This session is very sensitive. And when we're done with this, you have a very good understanding of how agentic workflow works. And you'll be able to implement a very good production grade architecture, even for a banking app, which is a very, very sensitive part because now we're dealing with user funds. And if you're dealing with user funds, you have a very production ready. And you have to also be able to use the very best production architecture when you're creating your framework. The next aspect we're looking at is the observability stack. So you must track the STT latency, the speech to text latency. You must track the GPT-4 time to first token, TTFT, as I previously mentioned. I hope everybody remembers that. TTFT, time to first token, the time it takes for our LLM to produce its very first output token based on the recent data. Then we're looking at the TTS, the text to speech. So we looked at the speech to text, down the text to speech, latency. So all these multiple areas are very much to be considered. The tool execution time, the error states, the token usage, the cost per session, the logs, the structured conversation turns, the tools input and output, interrupt frequency. And these are all things we have to observe, observability for production debugging. We have to have the ability to, for example, say, during a tool call pipeline, for example, the user wants to make a transfer, but instead, does our LLM agentic framework call, instead of calling the transfer tool, does it call the account tool, for example, or does it call the invoice tool instead? So we want to make sure that the system, our agentic pipeline is calling the right tools during function or tool calls. We want to also be able to observe the microservices that have been hit, the latency time, the reasoning process, the error state we're getting, the different sessions and logs, our conversation turns, accumulated entities via multiple conversation turns, and the context that has been injected for every processing cycle. So we want to be able to observe that. So this is a very elaborate, not so complex, but very technical system that you have to be very mindful of. Scaling the system. So we're looking at the LifeKit cluster, we look at that injects into our agentic worker pool, the LangChain orchestrators, our GPT-4 API, and back-end microservices. So when we scale in this system, he likes the image we have here. He's Roberts, the bands so much. So When we're talking about scaling, we're talking about how to make our system elastic, how to make it accommodative, so that the more requests we get and the more users we get in. When you now look at this, when you're starting from, let's say, 2 or 3 or 10 or 100 or 1,000 of users, the hits you're having on your server is minute. You can overlook some things and still have that very efficient latency. But when you begin to hit hundreds of thousands, you're hitting millions of users, concurrent or parallel tasks happening all at the same time, then you begin to see the downsides of not having very good scalable systems. So what is very production advisable, production grade architecture demands that you have all your services in a microservice architecture. Here you said about microservices before. So microservices give us a system where we have multiple services, multiple backend servers for multiple services, each server being independent. Most times, working with its own independent database, its own API architecture. However, because we are building a system of services, now called micro or small services, we also need to have a standard for all the services to communicate and share data. So this is a different topic of its own, but you have to make sure that your system is microservice based, and this helps it to be very efficient when it comes to processing high traffic of data, especially concurrent requests. Now, what are our failure modes? How do we handle failures during our conversations? How do we mitigate rolling window memory, keep raw history in database, inject only some? How do we handle all this? So how we mitigate our rolling window memory or conversation memory context window is by implementing structures like summarization compression. So our previous conversations, instead of passing that raw into the current conversation cycle to be processed again by the LLM, we can summarize that and inject that. We can also use tool result trimming. So the output from our different tools, we want to trim that so it's not so complicated. This will also improve it. Hack token, cut per session, context pruning. I've spoken about that before. We have to be able to prune context. By pruning, we mean what? Truncate context. And this is how most tools also work. We're looking at the Cloud Code, we're looking at GPT. That's why when you keep making multiple conversations in the same session, you see that sometimes it begins to do what? It begins to forget your previous conversations and it begins to sometimes hallucinate or drift away from the context of the conversation because the context window has become so big. So to optimize that to be efficient, you have to prune the context as it gets very large. Now, when pruning that, we have to be very mindful of the most recent conversations. So you don't prune the most recent. You always most times prune the extreme previous conversations, the very former conversations that most likely will not fit into the current context. So we also want to keep raw history in the database just in case you want to do audits, and then context inject only summarized states to our GPT-4 LLM. So very good way of handling failure modes. And mitigation, what happens when LangChain keeps appending data? User messages, tool outputs, memory, system prompts. When it keeps doing that, because the LangChain is the one that does all that, it gives us the framework that works with the LLMs to do that. Eventually, our LLM becomes the context window fills up, your costs skyrocket. So instead of paying, let's say, $200 per month, you're paying 1,000, you're paying 2,000 because the system LLM has processed so large a context window and outputted more equal tokens. And that's all counted for when you're using LLM APIs. The latency also increases because now it's reasoning more context. The cost spikes. The model quality degrades because now it's having too much to work on. The symptoms that you can use to know this is that from our observability, which we spoke about in the previous slides, and the auditing, we're looking at the time to facts token increases over time. The responses become vague, it's losing context, it's getting confuses, hallucinating. The token cost per session grows. You pay in more occasional truncation errors. So you must have to implement these security procedures, these optimization procedures to enable a very seamless stream. Once again, taking note that we're dealing with streams of data over the internet, the transportation, the reasoning, all that. And we want that to be very seamless, given that it's real-time in voice. Only the voice alone, the voice transition to text alone, and then back to speech is already a downtime, an overhead. So all this has to be considered in architecting your framework. Now let's look at cost engineering. The GPT-4 tokens, the speech to text. So once again, I hope everybody still remembers STT and TTS. So you will keep hearing STT and TTS through this pipeline of voice agentic systems, because this is what the entire framework is built on. So the TTS generation, the streaming bandwidth, the optimization, we're using GPT-4 only for reasoning turns, use smaller models, pre-memory aggressively. This is what we've spoken about previously. These are all means to cost engineer, to optimize costs, at the same time also giving very optimal output. The cache to responses, use adaptive sampling, predict cost per minute per user. So that comes into observability, that comes down into our observability and auditing system. The key takeaways. What are our key takeaways from all this conversation? I know that by now, I'm seeing so many people very smiling. I know that by now we've been able to get very good concept of how we can be able to engineer a voice agentic system. So obviously it's a little bit complex, but it is not complicated. It's complex. I always just say complex, and that the connectivity, the different requirements you need to connect might be a bunch, but it is never complicated, given that you understand how the system works. The key takeaways: the LiveKit real system, the LiveKit real-time backbone. This is what we use for WebRTC. Once again, you can remember what I mentioned about WebRTC, web real-time communication, end-to-end communication that removes our downtime. The Flutter cross-platform agent. You can remember what I spoke about Flutter. It's that framework for creating what? Mobile applications. Perfect. The LangChain orchestration, and then our GPT-4 LLM reasoning engine. This is the powerhouse of all the reasoning, all the stuff we're doing. Our LLM is the powerhouse. And one thing, as I mentioned previously, LangChain interfaces with multiple LLMs. GPT-4 was used for this case study, given that it's very good at reasoning, it's very good at tool calls, and it's not. I'm not just saying this. It's been benchmarked. It's been benchmarked on multiple tasks, and it's been seen to have very good tool call functionality and reasoning functionality. Thank you very much for attending this session. I hope that we were able to get very good, intricate, low-level details about how all this agentic pipeline works. We also building systems like this. My team and I, for example, are building voice agentic systems. And I can tell you that it's a very interesting architecture. Most times, you need senior engineers to be able to orchestrate this pipeline for you. But with this session, you have a very good understanding. So even if you're not a senior engineer, with this session, I've been able to break down to you the very low level. When I say low level, I mean the intricate back-end infrastructure pipeline or architectural flow that powers this house, that powers the audio synthesis. So whenever you see applications, for example, the LaserVault app, whenever you see apps like that work with audio streams, and you're just making conversations with the chatbot, and you're thinking it's magic. No, once again, that this is not magic. This is all technical. This is all tech. And if it's something you can understand, using this lecture you've received today, using the framework I've shared with you, you'll be able to create very optimized and optimal secured systems that are also able to serve millions of traffic, millions of hits, of concurrent hits, given that you implement the right architecture. So I'm very I'm pleased that it's my pleasure to have the session with you all, and I hope that you all understood the session and had a very good time. It is a very interesting subject. It's a very interesting pipeline, and I hope that you're able to go out there, implement this, and let's see the products you build. I love builders. We love builders. Let's have more builders. Let's have more voice agentic builders. From now on, when you hear about voice agents, don't be confused. It's not magic. It's not rocket science. It's just tech and architectural workflows. So thank you once again for attending this session. Thank you once again. You all are very lovely people. So I'll see you in the next session. Any questions before I go? Perfect. This shows perfect understanding. Perfect understanding. Very pleased once again to be in this session, and see you all in the next session. Bye.